Okay, so this is a lesson on rates, and we're going to look at, first of all, very quickly, the derivation of the rate equation. So I know you're both very, very good at maths, so you won't have any problems with this. So we're going to start off with the derivation and what the rate equation means. Derivation of the rate equation. Now, if you've got any problems during the lesson, please just raise your hand or do something, with the icons or whatever they're called. Okay, so we're going to do it from first principles, and that means right from the bottom. Okay, a plus, and there you go, I've already messed it up. A plus b gives me c plus d. This is an equation, isn't it? And obviously, on the left-hand side, we have things we call reactants. And on the right-hand side, things we call products. Okay, now, basically, the rate of an equation is very simply this. The rate of an equation is equal to the change in concentration of a species in the equation divided by, there, that works nicely, divide time taken, okay, for the change. Anything nasty there? Nothing nasty there? I'm going to assume you know exactly what I'm talking about unless I hear from you, okay? Now, don't forget, you can use the thumbs up and the thumbs down. So thumbs up for you, so far so good. Excellent, thanks Lungi. And thumbs down if things aren't so good. Okay, so what does that mean then? It means this, very simply. The rate of this equation above, the rate is equal to, well, it's the change in one of the reactants. Okay, I'm going to say the change in concentration of A, okay, divided by time taken. Okay. Now, what does that mean, though? All right, let's have a look. Let's interrogate that. Now, the change in concentration that we often call delta A, okay, that's the change in concentration of A, is equal to the concentration of A final minus the concentration of A initial. So, obviously, because A is a reactant, the final, this number is going to be smaller than this number. This one's going to be larger because A is a reactant and the concentration is going down. So bizarrely, delta A is going to give me a negative number, okay? Because it's a reactant. And therefore, if you have the rate, if you define the rate in terms of a reactant, what we do is we cheat and we get over this problem by just putting a minus there. Okay, so the rate in terms of A is equal to delta A divided by T, whoopsie daisy, and it's all minus. Okay, if we can now look at the rate with regard to a product, let's say C. Now the rate with respect to C, let's use a different color, is going to be the rate of change of C divided by T, but this is going to be a positive number, so we don't need a thing here. We just leave it as positive. So for reactants, we put a negative there, and for products, we put a positive there. And why do we put a positive? Well, because delta, change in C, is equal to the concentration of the final. Change in anything is always final minus initial. Minus concentration of initial. And because C is a reactant, this is getting bigger. So the final amount of C will be bigger, and this will always be smaller. Are we good there? Is everyone clear with that? Excellent. I'm going too fast, too slow, or just right? Just right. I'm assuming just right. Okay. It's a lot of wordy stuff. Thanks, Lungi. It's a lot of wordy stuff, but you know what? A lot of chemistry is, isn't it? All right, so we'll move this up a bit. Now, let's have a look at this. Let's put some stoichiometry into it. Okay, imagine we have this equation. A plus B gives me C plus D. Now, well, that's fair enough. So let me say 2A plus B gives 2C plus D. Now, because there's a 2 there, the rate of decrease of this, so the rate delta, the change in A and the change in B, that's supposed to be a triangle, all right, to show change in. These won't be the same because A will be used up quicker than B. Does that make sense? Because you've got 2 of these get used up for 1 of these. Does that make sense, guys? So even though we want the rate to be the same. We don't want different rates. I don't want to say okay, Helene. Right, I don't want to say this. I don't want to say I'm looking at this reaction, okay, and I want the rate of the reaction to be constant. Well, I want the rate of reaction to be the same, whatever vantage point I look at it from. Do you get that? I don't want to say if I measure A and it's going to go down quite as quickly as B, well, which is the correct rate? Is it the change in A or the change in B? And because there are different coefficients here, these are different coefficients, would you agree that A gets used up quicker than B? Oh no, but that's not necessarily true, dear. It's all a rate. It's to do with their stoichiometry, isn't it? Would you agree with this, dear? Let's have a look. Imagine C plus D. Okay. At the start, let's say I've got no C and no D. Okay. After, I don't know, let's say 5 seconds. How much C will I get? Let's say I get 3 of these. Oh, no, let's not use 3 because 3 is annoying. Let's say I get 4 of these. How much D will be formed then? If 4C is formed, how much D's will be formed? Exactly 2. And then after, let's say another 5 seconds. Okay, let's see. This is now 8, and this will be 4. Okay, so let's have a look at the rate here. Well, what's the rate of the equation? The rate is the change in C over time. But it should also be, well, let's do this one first. So rate of change of C, it's final C, which is 4, minus initial C, which is nothing, divided by 5. And that's going to give us 0.8 moles per decimeter cubed per second. Are you okay with that rate? Looking at this information here? Yeah. Okay, now let's pretend this is looking at the concentration of C. Now let's do it again, looking at the concentration of D. And now the rate is equal to the change in D divided by time. What's the change in D? Well, it's 2 minus 0 divided by 5. And it's 0.4 moles per decimeter cubed per second. Do you follow me? Is everyone good where I got these from? Now, guys, what is the rate of reaction then? It can't be 0.8 moles per decimeter cubed and 0.4 moles per decimeter cubed. Can't be the same, can it? So because these have different coefficients, one will grow faster than the other. And I don't want, this is confusing me totally. Is it 0.8 or is it 0.4? I don't know. It's 0.8 with respect to this, and it's 0.4 with respect to this. But what's the rate of reaction then? Well, we have to do a tricky little thing here. Okay, and this is, I don't think this is ever going to come up, but it's something that I think is important. So let's have a look at again. A plus B gives C plus D. And let's have their coefficients there as well now. I'm going to say this is WA, X, WX, Y, Z. And these yellow things are the coefficients. That's not how you spell coefficient, is it? It's only one O. These are the coefficients. So let's have a look at the rate of reaction now. Rate of reaction is equal to, let's do the products to make it easier. Okay, so it's the change of concentration of C, yeah, divided by Y, okay? And that will give you the same as if I use D. It is the rate of D divided by Z. These two should give you the same rates. So to give you the same rate, we have to divide it by the coefficient, okay? Does it work up here? Let's try it here. Well, there's the rate. The rate is now, there's the coefficient of C. So we can divide this by 2, and we get 0.4 moles per decimeter cubed per second. And this one, we divide it by 1. And it gives you 0.4 moles per decimeter cubed per second. Do you follow that? That's not an easy thing to understand, by the way, but do you get that? Because the coefficients are different, we have to treat the rates a little bit differently. It's not a nice thing, is it? It's a pain in the ass thing, isn't it? And this is something I think you should know. Yeah, look, guys, it's not easy. I promise you, it's not an easy thing. Okay, so that's how we deal with different coefficients. So the rates isn't the rate of increase in C might not be the same as the rate of the increase in D. But because we have different coefficients, one might be made quicker than the other, but we make it a level playing field. We make the rates the same by dividing by the coefficient. So if you divide by the coefficient, the rate becomes the same of them both. That's really complicated, and I hope you get that. But that's not a nice thing. But that's chemistry for you. What are you going to do? All right, so let's have a look at, we're still going to look at the rate equation. So all of this stuff is interesting, and I hope you get it. All right. I really do, because it's important that we get these things. But let's have a look at a bit of a derivation now. Let's have a look at A plus B gives C plus D. A nice, easy equation. And I want to examine this equation. First of all, I have to do it experimentally. I have to. This is not even a joke. We have to do this experimentally. And I'm going to do it like this. I'm going to do this reaction under different conditions. And first of all, I'm going to keep this guy, the concentration of B, we're going to keep this constant. And the concentration of A, we're going to allow to vary. Basically, it's going to go down, isn't it? Okay, because it's a reaction. So this is going to go down, but we're going to try and keep B constant. How do we keep the concentration of B constant? That's not a trivial question, because surely that's getting used up as well. Well, we can do it with what we call a large excess. Okay, now it's a funny term, isn't it? Large excess. But the fact is, if you see in an equation, if you see in a question large excess, it means very simply they're keeping this concentration constant. Okay, not the word excess, the two words large excess. It means we're keeping the concentration of B constant. All right, and we're going to vary A. All right, so, and we're going to do a graph here. Okay, there's a nice graph. I hope it's going to be a nice graph anyway. There's a nice graph. And I'm going to plot the concentration of A against time. And this is going to be in seconds, and this is going to be in moles per decimeter cubed. Now, as you both know, at the start of the reaction, it's going to be its most, it's going to be there, then it's going to fall a bit, and as time goes on, you'll get something like this. Okay, and now am I going to try and draw these together? I don't think I can with this program. It's not a great drawing program, to be honest with you. There's much better ones I should be using really, but I'm going to try. Let me try and drawing this together on my screen. So we're going to get. Oh, it's not great, is it? There. So do it, and now don't forget the concentration of B. We're keeping constant. Does that make sense? This is an experimental graph. We used an experiment to make this. Are we good? Are you okay with that? Everyone's good? All right, excellent stuff. All right, now, so that's good. And now, using this graph, I'm going to take a tangent there. I'm going to take a tangent there. And then I'm going to do a tangent there. So what are these tangents then? If you look at a tangent, it's rise over run, isn't it? So let's have a look at rise over run. So the tangent here, or let me draw one in the middle. It's easy. Whoops, daisy. Okay, something like this. Okay, and I want to find that angle there. And there's that one. That angle there. And there's this one. This is tiny, isn't it? And that angle there. And as you all know, I'm sure your maths is way better than mine. The tangent of theta is the slope, isn't it? It's the gradient. Or gradients. So, if you look at the units here, the slope is rise over run. So the units are moles per decimeter cubed per second. So the tangent of theta is the same as what we call the instantaneous rates. Okay, do you follow me by that? This is the rate at this time, this is the rate at this time, and this is the rate at this time. Well done, both of you. That's called the instantaneous rate. Now, we plot a derivative graph. We plot another graph here. This is graph 2, and it's known as a derivative. This is a derivative graph, and the derivative graph, oh, that's not good at all. Okay, let's draw the derivative graph, and here we go, there, and there. Now this graph, we plot the rates in moles per decimeter cubed per second against the concentration of A. Now, if you look up in this graph, concentration of A is the lowest, but the reaction is the highest. Yes? What am I talking about? Here at the right at the start, the concentration of A is the lowest. Yes. All right. And the concentration of A here and the concentration of A here. So we've got 3 rates. Yes. Now, the rate of reaction as the concentration of A varies. So as A is at, what am I trying to say here? A here, the concentration of A is at the highest here. So I'm going to call this A3. This one I'm going to call A2. And this one I'm going to call A1. And because this is concentration here, I'm sure you would agree, as you go up that way, the concentration is bigger. So the concentration, what I'm trying to say very, very badly, concentration of A3 is greater than the concentration at A2, which is greater than the concentration at A1. So when A is at its most concentrated, the tangent is at the greatest. So therefore, the rate of reaction is at the highest at A3. And then we have A2, say, down here. And then we'll say A1. Oh, these aren't the points, by the way. I've messed that up, haven't I? Let me get that. Let's say the point will be there, and the point will be there. And then this is A2, and this is A1. And I'm going to try and draw a graph very badly. I think my internet connection is bugging out on me here. All right, because it was better earlier. And there you go. We get a straight line graph. Ah, that took a long time. So when I plot rate against concentration of A, I get a straight line graph. So rate against concentration of A, I get a straight line graph. And if I get a straight line graph, we can assume proportionality. proportionality. So we can say the rate is proportional to the concentration of A. Is that clear? God, it's a long way round, isn't it? I didn't realise how boring my lessons are. You should complain. You should at least turn off. All right. Now we do exactly the same. So we can say from this the rate is equal to some sort of constant times the concentration of A. Now this only works when the concentration of B is constant. Okay, so what I do now, and I'm not going to do it because it would just kill us all, is I do all this again. Do all this again, and this time I keep A constant. Okay, and I find out that I find out the rate is equal to KB. Okay, oh, that's a horrible K. Let me get rid of that. Let me draw a nicer K. There. Okay, the rate is equal to KB. So and this is only when A is constant. Now I can combine these two graphs. I can these two equations, this equation and this equation, and I can say, well, the rate is equal to, let me call this K1 and this K2. The rate is equal to K1 times K2 into A times B. Okay, and a constant times a constant, believe it or not, ladies and gentlemen, is another constant. So we get the full rate equation there. Rate is equal to K times AB, and the coefficient of A is 1, the coefficient of B is 1. So we say the reaction is first order with respect to A. We say it is first order with respect to B, but we say it is second order overall. And that's literally 1 plus 1 gives 2. That's why it's second order overall. Does that make sense, all of you? I know I've been going on for way too long. Well done. I hope this is helping a little bit. I don't know if it is. I really wish it was. All right. Now, there's nothing to do here, but we've got to look at an example. Otherwise, we'll never know what's going on. So thankfully, I've got an example here. Obviously, I've got an example. So there you go. We're going to take a snapshot of this. Okay, and we're going to paste it there. I'm going to make that 100. Oh, it's not much different. I'm going to move this around. I want it nice for your presentation. All right, nitrogen monoxide reacts with oxygen to gas to form nitrogen dioxide. The following experimental data was shown. There, that, and that. Deduce the partial order reaction with respect to nitrogen monoxide and oxygen. Now, what do you reckon that they mean by partial order? All right, does anyone know? Anyone, while I'm getting my pen working properly? What do they reckon that was? No, Helene doesn't know that. Do you think, Longy, do you think you might know what that means? What colour should I use that colour? Well, it says partial order here. It means like this. This is a partial order. Okay, and this is a partial order. So a partial order is finding the order with respect to one thing and then finding the order with respect to a different thing. But the partial order is, well done, the order of each. Yeah, exactly, Longy. That's exactly what it means. So in this case, the equation I've just done up here, okay, the partial order is 1 with respect to the A. It is 1 with respect to B. So these are known as partial orders. Okay, but the full order is 2. This is the complete order or the full order. Does that make sense now, Helene? Are we good? Thumbs up, thumbs down? Good stuff. All right. So we've been given these. Now, all we're trying to see is the proportionality. That's all we're doing. I know it doesn't look like it, but this table is just another way of saying is looking at this graph here. Whoopsie daisy. This graph here. This graph. Okay. All we're looking for is proportionality. It doesn't look like it, but that's all it's doing. Okay. So now let's have a look then. I want to keep one constant. So which one am I going to keep constant? I can see using my special eyesight that this and this is the same. So I'm going to keep the concentration of NO constant. Okay, And that is equations or experiments 1 and 2. Experiment 1 and 2. Okay, and now I'm going to look at these. So going from here to here, what change is that? All right, obviously, I want to see the factor change. Now, how do we find the factor change? It's 1 divided by the other, gives you the factor change. And to do it, I personally always get the biggest one, and divide it by the smallest. So in this case, it's simply 0.06 divided by 0.03, which is 2. So there's a factor of 2 there. Why do I do the biggest divided by the smallest? Well, because it gives you a nice whole number, and our brains are better at whole numbers than at partial numbers. Trust me, they are. So this is, I've times that by 2. Now, what's the factor of the rates then? What's this? This. Again, I'm going to get the biggest one, which is 4.26 times 10 to the minus 2 divided by 2.13. That's ugly. Times 10 to the minus 2. And if you work that out, you'll get 2 again. So this is a factor of 2 as well. And in other words, I'm finding out this, aren't I? The rate is proportional to oxygen. Okay, and if I double the rate of the oxygen, if I times the oxygen by 2, the rate has gone up by 2. So that means the coefficient, sorry, not the coefficient, the exponent here must be 1 for that to take place. Does that make sense? I times 1 by 2, the other times is by 2. Therefore, the exponent must be 1. And therefore, it must be first order with respect to the oxygen. So the order, the partial order, as they say here, partial order is equal to 1 with respect to the concentration of oxygen. Okay, because I've doubled one thing, the other thing's doubled. All right, now I've got to get rid of, well, no, I don't want to get rid of this because I want this on the PDF at the end. I'm going to use these two, because these two I'm keeping the oxygen constant. Okay, so here now the oxygen concentration is constant. All right, and what do I do here? Well, from here to here, you can probably see it's a factor of 3. Okay, so this is a factor of 3. I've just done that by eyesight. Now let's figure out what this factor is. Well, we get the biggest, and the biggest is 1.92 times 10 to the minus 1 divided by the smallest, which is 2.13 times 10 to the minus 2. Now, I don't know what that is. I'm not clever enough to know off the top of my head. So I'm going to get a calculator if I can. Oh, there's one. I've got one right in front of me. Right, here we go. So I get 1.92 exponential minus 1 divided by 2.13 exponential minus 2. And I get 9. Wow. Sorry, 9. Yeah? So this is 9. Oh, bloody hell. Are you with me? Is everyone with me? Excellent. Well done. Am I going to start, or is this okay? Is this lesson all right for you? Because I don't want to go too easy. I want to be, I want to do things that are important for you. Is this working? It's okay. Yeah, I think the annoying thing with you two, you're just too nice, aren't you? If I'm doing simple stuff, you wouldn't say it, would you? Right. So now this is 9 times 9. So now the rate is proportional to the NO. Now this has gone up by a factor of 9 when this thing's gone up by a factor of 3. Yes? Now, how is that going to work? What must this exponent be for that to work? All right, I want this to equal this, and I want this to equal this. So for that to work, the exponent here must be 2, because 3 squared is 9, isn't it? So it must be, hold on guys, the